So guys, here we go. What we're going to do today, and this actually tends to go fairly quickly, is we're going to talk about what happens when gases mix together. Now, we got a little bit of a taste of this previously in lab when we talked about this idea of collecting gases over water and the two mix together and how do they play together and their pressures add up and things like that. But guys, here's the danger of today, and I'll be honest with you, this is also one of the things that I struggle with most to teach, because we're just going to lay these things out as being fact. We're going to say, here's Dalton's law of partial pressures. And you're all just going to go, yeah, that makes sense. I get it. And then we're going to solve some problems with it. And everyone's going to go, oh, that makes sense. I get it. But guys, the AP authors are masters at asking you questions that pick holes in things that you thought you actually understood. So I tell you this to say, when you get into the homework and when you see these questions in March, when we start doing practice questions for the test, don't be surprised if these questions seem harder than you initially thought they were. It's just one of these concepts that you really don't understand how complicated it is until you really start to chew on it. So anyway, guys, today is all about mixing gases together. And when we talk about mixing gases together, it all comes down to this. So this is where you want to start your notes. It comes down to something that is called Dalton's law of partial pressures. And guys, it's really this simple on the front. Dalton's law of partial pressure simply says the total pressure of a mixture of gases is equal to the pressure of each of the components of the mixture. That was paraphrasing. Or it says the total pressure of a mixture of gases equals the sum of the pressures that they would exert as if they were present alone. So if you have if you have a mixture of gases, and if you know the pressure of one gas, and if you know the pressure of the other gas, they add up to give you the pressure of the total system. And you go, yeah, that kind of makes sense. Until you really start to think about it. And then you find out it's maybe not as obvious as you think it should be. So guys, I'm going to try to show you why this isn't really intuitive as you start to get into it. But let me give it to you mathematically first. And guys, it says this. And we found out, and let's find it on the AP cheat sheet. This isn't exactly what it looks like on the equation sheet. Because on the equation sheet, they use A's and B's. Did they go as far as C? So on the equation sheet, they say PA, PB, PC. Our book, I believe, goes 1, 2, and 3. It doesn't matter. All that it's really saying is the pressure of A plus the pressure of B plus the pressure of C gives you the pressure of the entire system. Seems straightforward, right? You okay? So guys, let me show you why in my little world this actually doesn't make a whole lot of sense. And it goes like this. This is kind of the best that I can do. So let me lay it on you this way. So guys, this is how, remember, I think of gases. So we've got a gas on the left we're just going to call the red gas, and then the gas on the right that we're going to call the blue gas. So what we need to know in order to make sense of Dalton's law of partial pressures is we need to know the pressures of these two gases. Now guys, let's assume the volumes are the same. And they are, because I drew the circle and just copied and pasted it. And let's assume the temperatures are the same, because we'll pretend they are. But then guys, what about this? Which one of these two gases would have a greater pressure? The red or the blue? Why the blue? There's more particles. Now guys, what if you had to explain why more particles produce a greater pressure? How could you get there? Okay, so let's talk about that. And guys, this is interesting, and I'm going to call you out a little bit on that one, Caleb, but let's talk about it. So if we get PivNert on the board, so to speak, guys, look at what we said. We said that the volumes are the same. We said that the temperatures are the same. We know that R is a constant, right? So which one contains more moles, the blue or the red? The blue, more particles, right? We measure particles in moles. So more particles would mean more pressure. Now guys, here's the thing. If you were to write that on the AP test, you would only get one of the 2 points possible. If the question said, which one of these gases would have the greater pressure, assuming that their volumes and temperatures are the same, if you said the blue gas, because Pivnert verifies that or whatever, because of Pivnert, you'd only get one of the 2. Guys, why would they not accept Pivnert as an explanation for why the blue has a greater pressure than the red? No, it's even more fundamental than that. So guys, think about what we're doing. Explain why blue is greater pressure than red. And if we said because of Pivnert, why won't they give you the point? Say it again. That's math. But isn't math okay? Yeah, guys, math, and we talked about this on the last test. Math is never an explanation for a phenomenon. It's a description. So Caleb, you're right that Pivnert describes the phenomenon, but it does not explain the phenomenon. Do you see the difference? We're not splitting hairs. Just a second. We're not splitting hairs here, guys. You really cannot explain phenomenon using math because these molecules can't do math. So you've got to explain it with a particle explanation. So go ahead. They wouldn't give it to you. No, the question is why? Why do more particles create a greater pressure? Go ahead. Yes, more collisions. See guys, remember we talked last time about pressure being a function of force divided by area. And if you've got more particles, and you said that very well, if you've got more particles, you've got more collisions with the wall. More collisions will give you a greater force and therefore a greater pressure. Do you see the distinction? And guys, you got to be careful about that. You can't use equations to explain things. You can use it to describe things, but it's got to come down to that fundamental particle understanding that says because there's more particles, there's more collisions, therefore a higher pressure. Do you see the distinction? Okay, but that really wasn't the question we were trying to address. But guys, let's do this then. Let's just make up numbers. Let's say that this has 1 atmosphere of pressure, and then we'll, I wonder, 245, 246, oh, look at me. Yep, exactly twice, so the pressure will be twice. So, and is that true? If there's twice as many particles, will the pressure be twice as much? It actually will. You can see that in Pivnert, that the proportion is as moles double, pressure doubles if everything else is constant. So are we okay with the idea here so far? Now here's the question. Guys, what happens to the pressure? I think this will work. What happens to the pressure when we do that? It's just dragging things, y'all. So what happened to the pressure? What is the pressure now inside the vessel? And really, fundamentally, understand what we did is poured them or mixed them together into one container. But what would the pressure now be? 3 atmospheres. That's Dalton's law of partial pressures. But guys, here's why that doesn't make sense to me. Here's the idea. If I could take... No. There we go. Okay. If I could take this gas and if I could put it in an empty container, it makes sense in my brain that if I took this gas and put it in another container that was empty, then the pressure would be the same, right? But if I'm putting this gas in a container that already has gas in it, if this container's not empty, then it seems to me like putting this gas in this container would cause the pressure of the red gas to be more than 1 atmosphere because it's being squeezed more because it's not being put in an empty container. Does that make sense? Do you see where my brain goes with this? But guys, what's wrong with my logic in thinking that the pressure of the red gas would not be 1 atmosphere, but it would be something greater than that? Why isn't it something greater than that? Or do you not even have the same issues I do? Yeah.
Because it's not getting squeezed because it's so small.
What's so small?
The particles of the glue.
And that's the deal behind Dalton's law of partial pressures. Guys, the trick here is that when you put red gas into blue gas, red gas doesn't even know that blue gas was there to begin with. When you put red gas into blue gas may as well not even be there, because as far as red gas knows, that container is empty, even though blue gas is actually already in there. So why is it that they behave that way? And Jared was right on it. They behave that way because the particles are so spread out and they're so small that they functionally behave as if the other gases aren't even there. So as far as red gas knows, blue gas isn't there. As far as blue gas knows, red gas isn't even there. And so their pressures truly do just add up. Does that make sense? Is that... To me, it took me a long time, I don't even remember learning this in high school, but when I learned that in college, I wrestled with that for a long time because I really was thinking, if I'm putting red gas into a container that already contains blue gas, the pressure should go up more than just adding them together because they squeeze each other. You know what I'm saying? But they don't. The pressures actually just add up because they don't know the other's there. Is that okay? Go ahead. Yeah. This is assuming they don't react. We're going to get into what they do if they do react later through the lens of Le Chatelier's principle. So if these things do react together, how does that change the pressure? And how would a pressure change affect the way they react? But we're going to get into that in like February. So that's a good point though, Jared. We're assuming that they're not reacting. Yeah, good point. Are you really okay on the concept? Okay, so let me see if I can get rid of this, and I don't think it's critical that I move this back, but I will. And then guys, we can go back here. And now it sounds like you feel like you have a more complete understanding of what this is saying. That the total pressure is the pressure of red gas and the pressure of blue gas added together, and they really do behave as if the other gases were not present. Is that good? Okay, so guys, with that fundamental understanding, what we can do is we can use this relationship to actually study mixtures of gases. And when we do that, we do this through the lens of the ideal gas law, which remember is Pivnert. So it goes like this. Don't write it down yet, but just sort of let it soak in. So this, guys, is actually just a retelling of Dalton's law of partial pressures. So this equation is this equation. Do you see the connection? If you don't, please work. I hate this thing. You know what we're going to do? When I get my new board, we're going to get together after school and we're going to burn this sucker. I'm so sick of this. Okay, Pivnert. Okay, so guys, when we take Pivnert and we solve it for pressure, we end up with this, right? So the pressure of a gas is equal to nRT divided by V, which is this. So the pressure total is the pressure of one gas as described by this, and the pressure, is that okay? You're okay algebraically to do that? Okay, so now guys, watch what we can do. So let me go back here, and then let's make sure you make the connection. So guys, what do we know about each one of these gases if Dalton's law of partial pressures is coming into play? Well, we know they're all in the same container, right? Because Dalton's law of partial pressures tells us that these gases are mixed. Does that make sense? So if these gases are in the same container, and if these gases are mixed, what do we know about the volume of each one of these gases? They're the same. Therefore, functionally, this cancels. And again, you don't need to do the math. Now, guys, or do this with me. And then R is a constant, so it factors out. What do we know about the temperature of each one of these gases? Also the same. So guys, if all of this stuff goes away, look at the proportion that we now formed. Now what we know is this. The pressure of a mixture of gases is proportional to what? What's left? Moles and moles and moles. And so guys, it turns out that we can leverage this relationship. Because if we know the total pressure of a gas, and if we know the number of moles of gas, we can figure out the pressures of those gases. Does that make sense? Let me show you. Let's go back to our pictures. So let me clean this up. Let me go just down. And we're going to play with it here, but we're not going to animate this anymore. Well, actually, no, we are. Ooh, this will work great. Let's do this. Okay, so we'll go back here. Now, you've already seen these drugged together. So let's drag them together, put them in the middle, and then talk about them like this. Okay, so guys, let me explain to you what that math was telling us. You ready? So let's do this. Do you remember how many red dots are there? There's 5, right? So let's say that 5 dots represents, oh wait, we can even color code this. Let's say that 5 dots represents 1 mole of gas. So guys, if there's 1 mole of red gas, then how many moles of blue gas are there? 2, because it's double, right? So there's 2 moles of the blue gas. So how many total moles are there? 3 moles, right? Now, oh, wait a second. If I were to write, okay, I'm going to try to write up here. Now, guys, let's do this. What would be a good number? Let's say 6. Say that we know the pressure of this entire system is 6 atmospheres. Here's the question. What's the pressure of the red gas? And what's the pressure of the blue gas? Here's how you know. You ready? The idea is this, and I'm going to switch to black so it doesn't look like we're talking about either one. There's 3 total moles, right? So what that means is 1/3 of the gas is the red gas by moles. It also means that 1/3 of the pressure will be the result of the red gas. So 1/3 of 6 is, of course, 2. Then, if 2 moles of the gas is the blue gas, 2/3 is blue, so 2/3 of the pressure would be from the blue, and that would be 4 atmospheres. Do you get the idea? So the idea is the ratio of moles and the ratio of pressures in mixtures of gases are proportional. You get the idea? Okay, so guys, let's say that formally by doing this. Back up here, and this is the idea. It says this, the pressure that a gas contributes to a mixture is proportional to the number of moles that it contributes to the mixture. It actually went pretty well. Yeah, you know, the sad part is I actually can't. Anytime you have school property that you're no longer using, you have to surplus it, and then they send it to American Fork and they shrink wrap it and put it on a pallet and put it up for auction. The thing that's ironic about that is American Fork is actually head and shoulders ahead of us in terms of technology integration. Yeah. No, they do some really neat stuff with technology up there. So do you get the idea? You good? All right. So guys, as a result of this, we can now solve questions like this. and I'd like to give you a chance to solve this. You're going to find that this one's pretty straightforward, but it is a question not unlike sort of a question that you might see on the AP test as a smaller part of a bigger question. It says this: you have a mixture of gases that contains 6 grams of oxygen and 9 grams of methane. You put it in a 15-liter container at 0. What is the partial pressure of each and the total pressure of the vessel? I'll give you a couple minutes to work on it, and then, guys, we'll solve it together. It's CH4, yeah. Yeah, and methane, interestingly, methane is one that they would expect you to know, but we haven't got there yet. We're going to do an organic unit. Typically, it happens over spring break. There are some fundamental hydrocarbons like methane that you do need to know. You basically just need to know methane, ethane, butane, propane, and a couple of their isomers. But interestingly, Caleb, your question segues well into what we're going to do at the end of class today. We're going to go shopping. You guys close? I'm gonna just sort of, well, I'm gonna see if my board will even let me do this. kind of fun to solve this question if they didn't ask you what was the partial pressure of each gas. If you're just going total pressure, you could derive, never mind. You could put them together and derive a new equation. So guys, why did we write piv inert twice? Because you got two different gases. And so really what you're doing is you're finding the pressure of each gas and then leveraging Dalton's law of partial pressures. So we are solving for pressure in each case, which is kind of new. We haven't done a lot of solving piv inert for P, but P is our variable, and then our volume in both cases is 15 liters. Now guys, number of moles, it's not given to us. So what do we have to do? We got to solve for it. Now you could use dimensional analysis to do this, but we know that the number of moles is equal to the mass divided by the molecular mass. So I would propose to you that you could actually just do this. Go 6 grams divided by 32 grams for the oxygen, and that would give you the number of moles, which is functionally what you do if you did the dimensional analysis. Yeah, okay. Then guys, I'm gonna quickly run out of space. So which is the right value for R? I guess it's up to us, right? We could use 8.31 or 0.08206. If we use the 0.08206, it would give us the pressure in atmospheres, so I'm gonna do that. So 0.08206, and guys, we should put units on that, but I don't have space. And then our temperature is 273 Kelvin. And then guys, we would repeat that process for the other gas, which is the methane, except for the mass factor would be 9 grams divided by 16 grams, because methane is CH4. And then we could find the individual pressures and then add them up to get the total pressure. But given that I'm so pushed for space, can you guys just give me the answers? So the pressure of the oxygen is 0.84 atmospheres. Did you? Oh, the methane is 0.8. Methane's 0.84 is 0.28, and so you added up 2.06. 1.12, sorry. That's what I, yeah. So 1.12 total atmosphere. Is that, you okay with the idea? Okay. All right. So guys, do you need more time to crunch through the numbers? It really at that point just becomes algebra, right? So one more thing to talk about, and then we've got something else to talk about that's a little more general, and then you're gonna have time to work on homework. You good? Okay. So guys, continuing with this theme of mixtures of gases, we have one more concept that we need to talk about, which we haven't talked about at all yet. This is something that you can say is uniquely brand new to AP. It isn't something we talked about in the past. It isn't something that we've really talked about up until now, except for we sort of alluded to it a minute ago when we talked about the proportionality between moles and pressure. So guys, here's what we know right now, and this is how it kind of supports the concept of mole fractions. So we know that if we know the pressure ratios of a gas, a mixture of gases, we also know the mole ratio of the gases. You okay with that idea? Okay, so let's take that and we're gonna do some playing around. So guys, we understand, and don't try to write this down, we understand that in a mixture of gases, these gases behave independently. They don't interact with each other. So here's what we can do. We can take piv inert and again solve it for pressure. And then we can create ratios that are not one gas and another gas, it's one gas and the total amount of gas. So it goes like this. If we want to know the ratio of the pressure of one gas to the pressure of the total gas, we can rewrite that ratio like this, because P is equal to nRT divided by V, and P is equal to nRT divided by V. And again, doing the same canceling that we did before, if these gases by definition are in the same container, then these cross off, and this is what we're left with. So here's what we know. the ratio of pressures of one gas to the total mixture will be equal to the mole ratio of one gas to the total mixture. So guys, we're going to get rid of this and collect the pieces here. So the pressure ratio is equal to the mole ratio. Now this mole ratio is actually called X. And if you grab your AP equation sheets, let me show you where this is. So under gases, liquids, and solutions, the second equation down, right underneath Pivner, tells you that X is moles of A divided by total moles. So guys, that's this. Moles of A divided by total moles is equal to X. Now guys, watch what happens. If we take this moles of A and if we replace it with X, we get this. See what I did? So take this and replace it with X, and then as your equation sheet does, solve this for the pressure of A and you get this. That the pressure total times the mole fraction gives you the pressure of A. And that's what you've got here. The pressure of A is equal to the pressure total times the mole fraction of A. So what does that mean? Well, guys, let's go back and let's talk about what that means going back to our original picture that we drew like this. Because, guys, really all that it is it's a reformulation of the concept we talked about here. So let's review. Guys, how many moles of A do we have? Do you remember what we said? 5 dots. We said is 1 mole. And then how many moles of B did we say we had? Twice. So we said 2 moles. And then we said that the total pressure here is 6 atmospheres, right? And we've already talked about the concept that actually leads to this equation that we're sharing now. So here's what it says. It says that the pressure of A is equal to the pressure total times X sub A. So watch what happens. What is the pressure of A? Well, that's what we're solving for. What is the total pressure? 6 atmospheres. Now, what is X sub A, which is the mole fraction of A? Well, the mole fraction is the moles of A, which is 1 mole, divided by the total moles, which is 3 moles. And so 1/3 of the moles is from A, so 1/3 times 6 is 2 atmospheres. So guys, that equation that we just derived in a couple minutes ago is actually just the mathematical representation of a relationship that you already said you were comfortable with. You get the idea? And that's it. So there you have it. You're going to have some opportunities in homework to apply that equation and fiddle with it, but that equation is simply just a retelling of this. So guys, here's what we're going to do. You ready? Here is your homework. And it really is just about this short. It's not a ton. 6 and 7 are conceptual, and then 63 through 73 are mathematical. Got it? So 6 and 7, 63, 67, 69, 73. Good?